Okay, so on your handout, you've got a graph of a function, and you've got a section where that function is decreasing or going downhill if you look at it left to right, a section where that function is constant, and a section where that function is increasing. So this is we'll call this the f of x function, all right? And the way that we're going to identify the calculus connection to increasing and decreasing is the slope. And we know in calculus that when we're talking slopes, we're talking derivatives. So a function is decreasing when the derivative of that function is less than 0. When the slope is negative, and you can see if we did like a little tangent line slope, a little tangent line drawn to the graph, that would be a section with negative slope. So wherever our function's derivative is negative, we know that section of function is going to be decreasing. Okay. We know a function is at a constant value when the derivative of that function is equal to 0. Okay. I'm going to make a little note here. The derivative equal to 0 is also potentially a transition between increasing and decreasing. And then the increasing side, if we have any increasing sections of a function, that's where we would have a positive slope, or where f prime would be greater than 0. So increasing, first derivative is positive. Decreasing, first derivative is negative. Constant, first derivative is 0. Basically, we identified this exact same thing with velocity. Velocity increasing when acceleration, its derivative is positive. Velocity decreasing when its derivative, acceleration, is negative. Velocity constant when its acceleration is 0. The numbers where we transition from decreasing to increasing, or decreasing to constant, or constant to increasing, or increasing to decreasing, whatever the transition is, the separating numbers we can call either critical numbers, or some textbooks call them critical values. So the critical values are going to be the numbers that help us figure out what parts of the function are increasing, what parts of the function are decreasing, what parts of the function are constant. By identifying critical values, that gives us the potential changing spots. Now, critical numbers are super easy to find. Okay. A critical number, or a critical value for a function, are the values where the derivative of that function is equal to 0. I'm going to make another note here. It's also possible to have a critical value when your derivative is undefined, but we're not really talking about that scenario yet, so I'm not going to worry too much about that. So my derivative equal to 0 is going to be our initial focus for critical values. So we're not going to look at any functions yet that would have a derivative that would be undefined. Most of our functions are going to be based around certain applications, and those certain application functions, formulas, aren't going to have undefined derivatives. Okay. So step 1 for any increasing, decreasing analysis problem is going to be identifying critical numbers, identifying where the derivative of the function is equal to 0. It's these equal to 0 potential spots that tells us, oh, we're going in from, we might be going from decreasing to constant, we might be going from constant to increasing, we might be going from decreasing to increasing, we might be going from increasing to decreasing. Okay, so step 1, find the critical numbers. We're just going to practice that. And so the first thing I have to do to find a critical number is find the derivative and set it equal to 0. That's kind of an old calculus joke. If you're not sure what to do in a calculus class, take the derivative and set it equal to 0, because we use that for a lot of problems, which is true. There's a lot of things we can do, a lot of things we can figure out from where the derivative equals 0. So my function here, x squared plus 5x minus 6. So luckily, nothing too exciting here. No product rule or quotient rule or chain rule or anything like that. We can just take our derivative power rule on each term. So 2x plus 5 is my derivative. Okay. And so then, in this case, since my original function is quadratic, my derivative is linear. Pretty easy to set a linear function equal to 0 and solve. That's a straight up algebra 1, even pre-algebra kind of skill. So 2x plus 5 equals 0, 2x equals negative 5, x equals negative 5 halves. Okay, everybody okay with that? Yep. Okay. So let's talk about what that means. That means I know some things. I know about this parabola. First of all, I know it's a parabola that looks like that. Okay. I know it's a parabola because it's an x squared. How do I know it opens up? It's got that positive leading coefficient. And here's what I know. This place right here where it goes from this side being a decreasing to this side being an increasing, that happens at x equals negative 5 over 2. That point right there is the point where x equals negative 5 over 2. That's where this function, and because I know it's a parabola, I haven't really officially tested that this is true, but because we know some things about parabolas that are kind of basic, we can just kind of jump to this conclusion. I know that the parabola is shaped like this, so the turn from the decrease to the increase, from the downhill to the uphill, has to be at negative 5 over 2. Now, did you ever learn anything about the vertex of a parabola? How to find it? If you talk about a parabola in this form, the vertex is always at when x equals negative b over 2a. Anybody remember learning that in Algebra 2? Sort of, maybe? Vertex form, negative b over 2a is going to, no? No? Okay. And maybe you guys don't talk about that anymore. If you did learn that, and that is something that sometimes is taught separately when you talk about parabolas and graphing parabolas, the reason that that's true is connected directly to the calculus. If we took this form of a quadratic, the derivative would be 2 times a times x plus b. And when you take 2ax plus b equals 0 and solve for x, you get negative b over 2a. So some of the things that you may have learned in the past, and different, last year was weird, and the year before, even at the end, was weird. So depending on what you learned about parabolas at a different point, if you've ever learned about the vertex, how to locate the vertex of a parabola, the trick that we use is connected directly to calculus, because any quadratic, any parabola equation, is derivative is going to fall into the same format. And so the x value, the critical value, is always going to come out to be the same number. We don't want to know this just about a parabola, though. We want to be able to do this for any function, so that functions that have multiple terms, like higher degree polynomials do, something that has 2 or 3 or 4 terms, we have the ability to determine exactly where those terms are. Those changes from decreasing to increasing or increasing to decreasing at the critical number. So is everybody okay with how I determine negative 5 halves as my critical number? Okay. Using calculus, this is the equation of the function. I take the derivative, set it equal to 0, solve for x. That tells me that is the point where this potentially changes from decreasing to increasing. All right, so take number 2. And you just find me some critical numbers. Okay. F of x equals 9x squared minus 2x cubed. So that is not a quadratic. It's actually a cubic function. Find me some critical numbers for that function.